Well, let's continue mathematical induction. 5.3 is going to be similar to what we did in 5.2. So we're just going to be using induction, but we're going to prove different things. So this time, let's prove divisibility. Okay, so let's just go straight into the examples using the theorem we learned in 5.2. Okay, so 5.3.1. Second. Example 5.3.1. Proving a divisibility sorry, got distracted there. All right, so here's the question. Use mathematical induction to prove that for each integer n greater than or equal to 0, 2 to the n, or 2 to the 2n minus 1 is divisible by 3. By 3. Okay. So let's use our step 1, right? So step 1, we will show 2 to the 2n minus 1 is divisible by 3 when n equals 0. So that'll be our first, our step 1, using some fixed number, right? So 2 to the 0 minus 1 would be equal to 1 minus 1, which is 0. And technically, the 0 is divisible by 3. And so now we do step 2. All right, step 2. So suppose 2 to the n minus 1 is divisible by 3. We want to show that 2 to the n plus 1 minus 1 is divisible by 3. So I'm going to use this to prove that guy, right? Oops, I should have a 2 right here. 2 to the 2n times n plus 1. Okay, so if I suppose that this is divisible by 3, so let's see, let's work with this guy right here first. We want to show that this is divisible by 3, so let's try doing some algebra to help us out. So that would be equal to 2 to the 2n plus 2 minus 1, which is equal to, and that is the same as factoring out a 2 squared, right? Which is the same as 2 to the 2n times 4 minus 1. Okay, so now we just need to see if we can, that should be 2n right there. Sorry about that. Now, how do we use this guy in here? Okay. That takes some thinking here. I don't see it right away, but remember, what we're trying to do is show that this whole thing is divisible by 3. Once I show that, then great. I need to somehow incorporate this. So let's try to do some algebra here. So there's 4 of these. So I'm thinking if I subtract one of them, then I'll have 3 of them, right? So subtract one of these right here. And so I'm basically breaking a piece off. Does that make sense? Right. 2 to the 2n plus 2 to the 2n would be 4 of them. So 3 plus 1 more of these is 4. So this is equal to that. Right. Now 2 to the 2n times 3 plus 2 to the 2n minus 1. Now we see it. So since 2 to the 2n times 3 and 2 to the 2n minus 1 are both divisible by 3, then 2 to the 2n plus 1 minus 1 is also divisible by 3, which is what we wanted to show. So there's step 2. So sometimes it takes some algebra and some, out of the box thinking. I mean, that wasn't too crazy hard, but when I first looked at this, I had no idea how to make this look like this one, right? So I was trying to use this somehow. But once I removed one, I figured if I change this to a 3, obviously this is divisible by 3 because it has a 3 in it, right? This minus 1, we said, is divisible by 3 because we supposed that. That was our inductive hypothesis, according to the book. That's what it's called, right? Because we're supposing the n is true and we want to prove n plus 1. All right, let's see. Let's try another one. Okay, now let's try proving an inequality. We've been doing equations this whole time. Let's try inequality. Use mathematical induction to prove that for each integer n greater than or equal to 3, 2n plus 1 is less than 2 to the n. Okay, so we want to prove that 2n plus 1 is less than 2 to the n as long as n is bigger than 3 or equal to. So we'll do this with induction again. So step 1, I'm going to use 3. And this time I would call P of n 2n plus 1 less than 2 to the n. P of 1 would be 2 times 1 plus 1. Is that less than 2 to the 1? That would be 3 less than 2. So yeah, wait. I'm sorry, they said greater than or equal to 3. So let's start with 3, not 1. Obviously, that's not true right there. That's funny. There we go. So that'll be 6 plus 1 is 7. Is 7 less than 8? Yes. The PO1 works. So now we will prove step 2. Or use start step 2. So suppose that this is true. 2n plus 1 is less than 2n. We will show that 2n plus 1 is less than 2n plus 1. Of course, we still have this restriction. N is greater than or equal to 3. Okay. All right, so let's see, let me think about this. Well, let's just start trying to do algebra. So we're going to start with this guy and see if we can use the hypothesis to show that this less than, or this inequality is true. Okay, so that'd be 2n plus 2 plus 1 less than 2 to the n plus 1, which is 2n plus 3 less than 2n plus 1. Okay, so that was 2. Yeah, that's right. Okay. Then let me start that part over. So we're using 2n plus 1. So I think I don't see it right away. All right, let's start with this piece. So we know that that's equal to 2n plus 2, right? And we know that 2n plus 1 plus 2 plus 1, right? Yeah. 2n times that times 1 plus 1. Now, if I rewrite it to make it look like the original, because I need to use the original somehow, that would be 2n plus 1 plus 2. So if I add 2 to both sides, then that means that I can for sure say that this is less than 2n plus 2, right? This is by adding plus 2 to both sides. So then I could say, well, this is technically less than 2 of these, right? Still true. Now, the only reason I did that was so I can add them together. So now I have 2 of them, right? Now, if I multiply them together, now we get 2n plus 1, which is what we wanted to show. So that shows us that this, the original, is equal to that, is equal to this, which is less than that, which is less than this, which is equal to this, which is equal to that. Therefore, this is less than this, which is what we wanted to show. So doing some weird algebra, right? We're trying to force it to become this. At first, I didn't see it, so I was looking at this and said, wait a minute, I need to kind of use this fact here. If I multiply it out, it looks like this with an extra 2. That's how I got to there. So then I said, well, I know for a fact that if I add 2 to this to both sides here, it would still be less than, because I didn't really change anything, right? 3 is less than 4. If I add 2 to both sides, we'd have 5 less than 6. So it's still true. See what I mean? So that's how I got to here. Then I said, well, I need to get n plus 1. So I need to multiply by 2. So I know that if I were to add another one with a power, it would, of course, be less than this one, because it's bigger, right? Add them together, combine like terms, gets us to here, which gets us to what we wanted. So yeah, step 2 works. We showed what we wanted to show. Pretty much it for 5.3. So what I'm going to want you to prove is a bunch of divisibility problems, like the first one we did here. Equals type. Like this, divisibility, and then a few either basic equations or maybe divisibility that have inequalities. So it's just stuff like that. All right, let's go move on to the next section.